Thank you. Hello, my name is Dharma Shukla. I was the one who started Cosmos DB project in Microsoft in 2010. And so I'm going to talk about what is Cosmos DB, the properties of the system, and the design choices that we made, the capabilities it offers, and so on. So this is the outline of the talk. I'll start with a little background of how we started. We talk about the constraints against which we had to build the system. You know, every system is designed against set of backdrop of a set of constraints. So we'll talk about the constraints, then talk about the capabilities, and then we'll dive in the design. I have a lot of content, a lot of ground to cover, so I'll go really fast. If I'm too fast, let me know and slow down. And then we'll have some time for Q&A at the end. So, you know, back in 2010, observing that a lot of internal applications within Microsoft at high scale needed a globally distributed database system. I had a prototype back in 2010, so probably, you know, 2009, 2010, I worked on a prototype system. And in the city of Florence, I took a vacation, and that's when the system finally started to work. And so I came back to Redmond, pitched this project to all the folks at Microsoft, and I had a couple of customers. They wanted to use it. And I was asked in one of the meetings, what is the name of this system? And I had no name for this, so I just called Project Florence. And that's how, that was the beginning. I threw away the prototype. We decided to rewrite everything in C++ all over again, and build a team, build the project. A lot of internal applications started taking dependency on the system. In 2014, a subset of it, we decided to expose it to Azure developers under the name DocumentDB. And over time, we kept adding more and more and more. And we reached a point where the name DocumentDB cannot contain all the capabilities that we have. And in 2017, in fact, last week at Build, we announced Cosmos DB. That's now exposing all of the underlying capabilities that we have been building for the last 7 years. It's one of the fastest growing services on Azure. It's used within Microsoft quite a bit. So no discussion on distributed systems or no talk on distributed system is complete without mention of Leslie. Leslie Lamport has been our inspiration. And all these years, we decided to build a system that is really robust. And we use TLA Plus, which is one of his contributions extensively. We also use a lot of the work that he has done. In fact, at this point, we feel that many of the design choices that we've made, one way or the other, accrues to the work of Leslie. So I have a short video clip that we recently shot with Leslie, in which he describes what Cosmos DB is. And it is one of the best definitions of Cosmos DB. It's music to my ears, so I want to share it with you.
Hello, we're here with Dr. Leslie Lamport, the Turing Award winner and world-renowned computer scientist. Leslie's work on distributed systems and TLA Plus has influenced and enabled many distributed systems, and Cosmos DB is no exception. Hi, Leslie.
Hello.
Can you tell us a little bit more about Cosmos DB?
Cosmos DB is a database system in which the data can be replicated and copies distributed throughout the world. This permits an application to be configured so every user is near a copy of the data without the application programmer having to worry about how many copies there are or where they're located.
And what are some of the novel contributions Microsoft Research made to Cosmos DB?
My TLA Plus specification language and its tools were used to improve the design of Cosmos DB, helping ensure its robustness. The Cosmos DB team credits TLA Plus with helping them provide great SLAs to our customers. The work of other researchers at Microsoft Research and elsewhere was crucial to developing the 5 different consistency models that Cosmos DB allows developers to choose from. Many consistency models have been proposed in research papers over the years, but to my knowledge, Cosmos DB is the only commercial system that has tried to identify the useful ones and implement them precisely.
We used TLA+, which is the language that and the tool chain that Leslie and his team developed at Microsoft extensively in writing the specs for many of the complex parts of the system. So these were the requirements against which we had to build the system. We wanted to enable global distribution as a turnkey mechanism. So a user can go on a map of the world and select a set of regions, and the data automatically starts replicating. And we have to give an upper bound of a duration by which the new region that we have onboarded comes to life. The users, the developers should be able to test the end-to-end availability of the entire application stack. So they should be able to simulate regional disasters at will. So you should be able to write, a line of code that says, I want to tear down this region, I want to bring this region online again, things like that, to test the end-to-end availability of the system. So that's a capability that we had to add. And that's what we mean by turnkey global distribution. The replication is automatic. You don't have to do anything. You don't have to write any code. You don't have to set up, clusters across different data centers. No configuration required. It just works. We want to give guaranteed low latency at the 99th percentile to wherever the users are. So all applications in Microsoft require, they need to be globally distributed. They have users all around the world. So we want to give at the 99th percentile what is the latency that the app can rely on. We want to give, of course, the high availability SLAs both within the region and across regions. And some definition of consistency, and we'll talk about this at great length. We want to give guaranteed consistency guarantees, and this requires, navigating the CAP theorem in all failure cases, and the low latency piece requires navigating the speed of light in a happy path. And the core requirement, the way the service is offered, or we wanted to offer to users, is that application developers should be able to provision throughput, should be able to, based on their needs, need throughput. If you say table.throughput equals, million transactions per second, that's a line of code you write. And across any number of regions where your table is distributed, you get 1 million transactions per second, you should be able to get. The next line of code that you write, you say, table.throughput equals 1,000 transactions per second. We need to manage all the partitions, do the merge of partitions worldwide, and bring it down to 1,000 transactions per second. So elastically scaling throughput, as we'll see, we learned a lot. It is a completely different ballgame than elastically scaling storage. And so the service is fundamentally offered to developers inside Microsoft as well as externally in terms of provisioning throughput. And for all of these things above, we wanted to give comprehensive SLAs. Most services, cloud services, provide SLAs for high availability. Very few of them, if at all, provide any kind of guarantees on low latency or consistency or throughput. And we know that as a globally distributed database system, you have to navigate all of these trade-offs, and we wanted to give clear guidance, clear SLAs for all of those 4 dimensions. Of course, as a cloud provider, we want to operate at a very, very low cost. So it's very easy to build, as we've learned, a system that you can throw many, many machines at it and provide all the capabilities, but we want to operate at very low cost. We want to leverage the cloud and different types of workloads that we serve in a very optimal way so that we can use the system resources in a manner that reduces the overall operational cost as well as capital cost. And we give all that money back to customers. Developers who write globally distributed apps, they need to not worry about schemas or index management. It's a nightmare to do alter table at such massive scale. So we want to just take away all of the burden of schema and index management altogether. And that required us to do a lot of heavy lifting. I'll describe that in detail. So the first, all of these collectively required us to build a globally distributed database system from the ground up. There was no system inside Microsoft or externally that we could take those pieces and sort of stitch it together and build this system. For example, we couldn't have taken a single site database system like SQL Server or some of these systems that we already had inside the company. We had to build a system that automatically distributes data and throughput worldwide, and that required us to build it from ground up. Resource governance as a multi-tenant system. The system, in order to operate at low cost and provide all these SLAs, had to be fully resource governed. So things from B tree to replication stack to transport to every part of the system, query processor, every aspect of the system had to be fully resource governed. That means rate limiting and back pressure is built in. You can think of the entire system as a gigantic queuing system. So that had to be done as well. And one of the things we realized during the course of this system, while we were building the system, is that every developer wanted a different data model and a different API to interact with the system. Maybe because they were using MongoDB and they wanted to continue to use MongoDB, and we didn't want them to rewrite their application code to use Cosmos DB. So we decided to settle on a data model that was the work that was done in IR systems a while back. And we took a data model that can, we can take graphs, we can take key value, column family, documents, and easily and efficiently map them to this underlying data model. That, coupled with the fact that we are completely schema agnostic, allows us to support a wide range of data models and APIs. So global distribution, as I mentioned before, so these are the list of capabilities that the system offers. I'll do a quick pass at this before we go into the design of the system. Cosmos DB is a foundational Azure service. That means that every part of Azure also takes a dependency on it. It's at the bottom of the stack. So it's by default available in all regions. Anytime a new region opens up in Azure, it's installed by default. And that has a certain properties around layering that it follows. It supports, as I mentioned, automatic replication, so you don't have to worry about setting up anything. You just effectively select a region and your data starts getting replicated. One of the interesting design choice that we made is that we made all of the entities that we expose very logical. So there is no notion of there's no notion of physical endpoints or physical addresses that you have to deal with. As an application programmer, you just program against logical resources, and we present a single system image of all the resources that we expose, all the entities that we expose to you. And so whenever there is a regional disaster, your app continues to work because you're programming against always the logical endpoints. You don't have to worry about redeploying your app. That's one of the crucial aspects, and a lot of work that has gone into how we present the programming model has ability to support multi-homing is one of the crucial design points. We allow developers to change the priorities of the region. So you can associate any number of regions with your database or your table, and then you can assign priorities to it. So you can say that US East is my number one priority, followed by US West, followed by South Central, followed by North Europe, and so on. So whenever the disasters happen, whenever there are failures, we transparently fail over in the order of priorities. You can change the priorities at will, and you can test the entire end-to-end availability of your application by triggering the simulating failovers or disasters. And we give comprehensive SLAs as part of this. Guaranteed low latency at the 99th percentile. We give you right now less than 15 millisecond at P99 for all the indexed writes, and less than 10 millisecond at 99th percentile for all the reads. Index writes have improved since this slide was done. It's now at the range of 10 milliseconds, but we're still hardening it, and our goal is to reduce the write latencies as much as we can. There are two aspects that contribute to guaranteeing the low latency. Number one is the design of the database engine. What we've done is that we've taken the best of log structuring techniques from the NoSQL databases. There's work in Microsoft Research on a system called Llama. So we've taken that work and we combine it with ledge-free B trees on the read path. And so we've created a storage engine that has the most optimal write amplification and read amplification in a multi-tenant setup. Because space is crucial on every machine that we run Cosmos DB, we want to make sure that we don't eat a lot of space in order to serve writes without any pauses as well as efficient reads. So that's a very crucial piece to guarantee low latency, the design of the storage engine. The other piece which is layered on top of it is the idea that we can ingest sustained volumes of writes without requiring schema or secondary indices, and can synchronously index everything we ingest, replicate synchronously within a same region, and durably commit on all the replicas. When we get a quorum ACK, we ACK the client's write. All of that stuff has to happen within less than 15 milliseconds. So this 15 millisecond at the 99th percentile is indexed writes. So it's not just the client has sent the write and we have ACKed. It is durably committed, replicated, and indexed. So again, the work that was done for translating records, any data structure that we get into tree, doing it, indexing the paths of the trees and things like that, contributed to making sure that we can give guaranteed low latency, especially for writes. The second piece, besides the database engine, which gives low latency, is the design of the replication protocol. And we make sure that as much as possible, the reads and the writes are always local to a given region. So we never try to meet the quorum by making calls across region. We make sure that the quorums are always local, and then we can serve reads and writes locally. There's nothing fundamentally groundbreaking about this. We take care of the partition management like any other horizontally partitioned system does. We allow you to scale a single table or a single collection any amount of data you want. We support TTL on documents or tables, so you can, or records or tables, so you can purge them. We have fancy policies that allow you to tier the expired documents to a remote storage, or you can just simply choose to delete. But the key piece of hard work, the hard work that took 6-7 years to harden and mature, is about scaling throughput. So this is the typical scenario. Customers want throughput worldwide, and they want to provision for what the provision throughput for what the demand is. And so what we've done is that we have the partition management that is done behind every table or every collection or every entity in a horizontally sharded system is done in a manner that is extremely responsive. So when you write this kind of, when you program against the system and you say, I want this much throughput, one line of code, and the next line of code, it says, I want 10 million requests per second, another line, I want 50 million requests per second. To deliver that much throughput worldwide, we have made it a metadata operation. So you guaranteed that you get that throughput, and the partition management happens behind the scenes at this high scale. So that's the sort of the secret sauce or the spine of the system. And we couldn't have done this unless the entire system was fully resource governed. There's another piece here, which is that the fact that the system is resource governed enables us to give provisioning capability at various granularities. So you can provision throughput at a second granularity, or you can do it at a minute granularity, or you can do it at an hour granularity. When you do that, you can predictably cope up with the spikes in your workload. So you provision, let's say, 1 million requests per second, and then you provision 10,000 requests per minute. So whenever, within a second, you exceed the provision per second throughput, we will borrow it from the minutes worth of budget and apply it to that second so that you can deal with spikes in a very predictable way. And you can monetize, the customers are willing to pay for all the throughput that they provision at different granularities. So when we're dealing with this kind of system, as you know, and as Leslie pointed out, we know this world really well. So what we have done is that we have mined well-defined consistency models such that you don't have to deal with these extreme choices. And the criteria for picking a consistency model from the vast array of literature is that it has to be useful, it has to enable practical real-world scenarios, and we've harvested many, and we keep testing it. The criteria is also not just useful and practical and enable scenario, but also we should be able to maintain the SLA at this high scale. We should be able to monetize it so the customers are willing to pay for it, and it's easy and intuitive and provides predictable guarantees. So far we have exposed 5 consistency models, and over time we are finding, so we view the consistency as a spectrum, and we think that we found 5 click stops along this spectrum. Over time, we are going to find the other properties of these consistency models which are nearby, in the nearby range, and we're going to add to these 5 that we have developed. So our goal is not to create a large array of consistency models and create more confusion for developers, but restrict it to a very small subset of consistency choices where we can provide guarantees and they enable real-world scenarios. So the 5 that we have, unfortunately, it's not visible from the slides. It is strong consistency at one extreme, eventual consistency at the other extreme. In between, after strong consistency, is bounded staleness. Bounded staleness means that it is, if the staleness is 0, then it is as good as linearizable guarantee. So bounded staleness says that for a delta T or K operations, the reads will lag behind writes. But it's total global order. It's monotonic reads within a region. And except for the staleness window, your universe is intact across any number of readers or writers. Session consistency is the next one after bounded staleness. It says that you get monotonic read, monotonic write guarantees, you get read your write guarantees within the context of a session. So it's partial order, streams of replication streams that we propagate. And session consistency is one of the most popular ones, as we've learned from running the service for some time. Followed by that is consistent prefix guarantee. That means that there's a global order that is preserved, and the prefix guarantees are ensured so that you don't get out of order reads. And the applies, the commits happen in the same order in both the write and the read region. And then there is the eventual consistency. So if we make it super simple, you can go to Azure portal under your account, you pick the consistency choice, and you configure it, and that's it. You don't have to worry about setting up quorums or replica set sizes or data center configurations, etc. And these guarantees are then maintained. You can always change your choice of consistency by calling an API. You can also override consistency on a per request basis. So far, are you guys with me? Does this make sense? And the interesting thing between the choices, the proofs in the pudding, 73% of all customers use session consistency. Bounded staleness is the next one. We don't have the telemetry for the consistent prefix yet because we just announced it. But eventual and strong are sort of on the fringes. So that shows that the customers do find these useful. This is the SLA. This is the only service, as I mentioned, provides SLAs. We transparently propagate all metrics to customers, let them see all the SLA violations in their dashboard, so they know if we've goofed up. So when you're building a globally distributed app, you don't want to deal with schemas, you don't want to deal alter table, but you want your queries to work. Imagine you're doing a rollout of your application code, you made some changes to your classes, and you stop your rollout midstream. What happens to the database schema and your application schema in this partial deployed state? There are many, many use cases where it's just not possible for you to maintain your database schema and the application schema in sync. So what we've done is that we've taken this approach of you can have any record. Anytime we see a set of text labels, we take all those labels and convert them into a tree structure. So in a JSON document, for example, every property name or a value that you see is represented as a tree structure. If you have a column family record, we do the similar thing. So there's a well-known transform that we apply, which will take a text record and translate it into a tree structure. And then we index the paths from the root to the leaves. We cut the paths. So imagine a primary replica receiving lots of writes. So it receives the writes within a 5-second window. We take all the records that we are ingesting and materializing them into trees, and then cutting the paths from the root to the leaf of all of these trees. And then the beautiful thing here is that a lot of the interior nodes of any tree, so the names of the property or the structure which correspond to the interior nodes, they are all the same in a small enough granularity of time. So within 5 seconds, for example, you'll find lots of records that are being received. They all have the same schema, or at least a lot of commonality across the schema. The variance comes from the values. So the instance values are always located at the leaf. So that provides a huge opportunity to do deduplication and do large sequential flushes on SSD for all the indexes, 16 MB worth of flushes. And so the writes become really, really fast. Everything gets indexed. All of the paths that we index get, they are encoded, they get compressed, and you don't really require any schema or second indices. You can, as a developer, you can opt out of this. You can say, I don't want certain records to be indexed at all, or I don't want certain paths across all my records to be indexed at all. You can do that. And when we do that, we do this in-place index transformations so that your availability or performance doesn't degrade, and you can transform seamlessly without taking more space on disk, transform the old index and the new index, and when the transformation is ongoing, if the queries come, we consult both the trees. So the net of all of this is that you don't have to worry about schemas or indexes. You just write your app, keep dumping data into tables, and we will automatically index everything, and so that you get SQL queries. Again, by virtue of doing that, we are able to support multiple data models, and there's also an ongoing quest of supporting more and more wire protocols and data models and covering large area of the data model space. So that's a simple sort of side effect of the previous techniques. Cool. So this is what the developers see. They see, the system is exposed in terms of, as a developer, you create a database account under which you create a database, under which you create, containers like tables or collections or graphs, and then you just add items to it. So internally, for every type of API that we expose, so if you're using MongoDB or using DocumentDB or using Gremlin or Azure Table Storage or whatever, we translate that resource model. That is the resource model that the system understands, and we project the spatialized types to developers. So the ones at the bottom, container and item types, are spatialized so that for every API that you use against Cosmos DB, you get, you feel you're dealing with graphs. So your container is a graph, and your nodes and edges are items. If you're dealing with using MongoDB API, your container is a collection, and the item is a document, and so on. So this is a logical resource model. It has every entity in this is URI addressable, and it is consistent. Underneath each of these entities is horizontally sharded, and you know the partitions are made highly available via replication. The partitions undergo a lot of churn, failures happen, but you keep getting a consistent image of your logical data model. So for example, if you delete a database, but you also have a URI reference to a table or a record, we make sure that regardless of the number of regions where your database is distributed, you cannot access your table or cannot access your record because your database is deleted. So that level of strong consistency is implemented and create this overlay of logical overlay on top of the physical partition resources. So across many customers, thousands and thousands of customers, each of these customers have many millions of such records and entities and resources. They're all horizontally partitioned based on the partition policies specified by the customer. And then each partition is made highly available and consistent using a set of replicas. The replicas, the membership varies, so it's dynamically adjusted depending on the failures. And correspondingly, the size of the quorum also varies because the replica set membership changes, the quorums calculations also change. There are some interesting things here. So first is that within a partition, within a resource partition, there is a distinguished primary set of followers, and one unique replica that is a very special replica. It's called forwarder. This forwarder is the guy who connects and sends replication packets to other resource partitions for a variety of reasons. Resource partition, think of resource partition as a Lego block of coordination. We have TLA plus specs around this thing. It's battle tested, and we use it whenever we need a coordination problem to be solved. We use this as a component, stitch it together, and multiple levels of consensus can be implemented on top of this one building block. And global distribution is one example of it. So, you know, any coordination decision like splitting partitions, merging partitions, multiple use cases exist. So resource partition is a Lego block. Everything across different tenants get horizontally partitioned into one of these things. Then each resource partition owning some set of keys is then distributed in another dimension. So in this example, I have a table or a collection or a graph, some container that is partitioned by a key called airport. And airport, depending on the value of the airport, I have 3 partition sets. So a partition set is a group of partitions, resource partitions. They own the same key range. And again, there is a guaranteed leader within a partition set. So this is an example of taking a resource partition as a lower level building block and building a higher level grouping construct on top of it. So again, each one is highly available. Each one is strongly consistent, all these resource partitions. And then the larger constructs that we build on top of it, they give corresponding guarantees. In this example, the reads and writes, you can choose within a partition set which partition is the master. And so failure detection, leader election happens in this example at 2 levels, one within the partition, resource partition, the other at a higher level within a partition set. So we use this all over the place. We use it when we have to migrate tenants, when we use it to do global distribution, we use it for partitioning, for many purposes. The physical topology of the system, so far so good. So far we are having fun. Okay, that's very quiet. So physically, this is what the world looks like. In planet Earth, different Azure regions, 34 plus regions. In each region, data centers, we get large stamps of machines for specific SKUs. And then these are spread across fault domains, and we make sure that all of the replicas within resource partitions, they're all spread across different fault domains. We typically run with, a fault domain is like a rack boundary. We typically run with 10 to 20 fault domains. And we build an overlay network called a cluster. Cluster consists of machines. Machine consists of container instances, and each container instance hosts a replica. In some instances, a set of replicas. Each replica hosts an instance of the database engine. And database engine consists of all of the good stuff: the query processor, storage engine, indexing, and is also has all of the logic for doing replication. So this is the larger topology. At logical level, all of those resource partitions and those forwarder replicas, they would connect with each other using different topologies. So depending on the network conditions, so for example, in the United States, a customer having a single table distributed across US, Europe, and India, and Singapore, and we know that the network conditions from the place where the writes are happening to India data center are depending on those network conditions and depending on the consistency level that was chosen, we dynamically adjust the topologies such that we can sometimes use chain replication, sometimes use hub and spoke. So effectively, it's a tree, and then we configure the topology dynamically based on the conditions at a given point in time. And there's a lot of communication exchange that happens between the receiver replicas within the resource partitions on the other side and the forwarder, such that we have ample understanding of the network conditions at any given point in time. So this is a partition set. Within each replica, so if you go back, here within a replica is a database engine. That database engine is designed such that the storage engine and the query processor and the index management can be decoupled and can be separated in distance. And it has wonderful side effects. So within, that is on the top, those three circles represent a partition set consisting of key range with some master partition. Within a partition set, each resource partition is made highly available by virtue of set of replicas. Each replica hosts the database engine, and the top part of the database engine, which consists of this logical index as well as different representation, columnar representation, row level representation, all of that, and the QP is separated from the storage engine by well-defined interface, such that depending on the service tier, depending on how much low latency you want for what price, we can separate the storage engine such that the storage, the actual storage can happen on the same machine and within the same process, or can happen in the cluster, or can happen remotely. So this allows us to give different types of offers to customers. Customers who want to scale raw storage without scaling sufficient amount of throughput can afford longer distance between the storage engine and the query. And customers who want really low latency and scale throughput opt for closer proximity between storage engine and query processor. The entire stack is resource governed. One of the challenges here is to take arbitrary database operations. This is a database, it doesn't just have key lookups. So if you have queries, if you have more complex operations, taking all of those operations and devising a normalized currency of usage. So for example, we call this normalized currency request unit. Request unit encapsulates some amount of CPU, some amount of IOPS and memory, and every operation that happens in the system is charged some amount of RUs. So within every second, everything that is happening in the system is accumulating, charging the RUs, which is the amount of system resources that are used. And customer provisions throughput in terms of RUs. We define an RU as if you do 1 kilobyte record, a point read on a 1 kilobyte record, it's 1 RU. And you provision, 1 million requests per second, that's like 1 million RUs per second. And correspondingly, we define other operations in terms of RUs. Every replica that you saw within a partition, which was a part of a partition set, every replica gets a fixed budget of RUs, effectively gets a fixed budget of system resources, and it has to live within its budget. So if a developer provisions 10,000 requests per second, we make sure that those 10,000 requests per second can be served by the replicas, the primaries, and the secondaries in a certain way, and they each get some fixed budget of RUs at that point in time, and they deliver that 10,000 requests per second. If the application pounds on those partitions harder than 10,000 requests per second, they get rate limited. If they don't use 10,000 requests in that second, we use all of the remaining budget to do background activities like running the GC on the storage engine or taking snapshot backups and things like that. So you can imagine that the entire system has to live within a fixed budget to deliver the throughput, to deliver all of the guarantees it has to. So it's finely calibrated and not a single mistake. A single mistake, a bug that goes in and gets deployed results into all sorts of bad things. This is another example where different granularity. I mentioned this is a case where a customer has provisioned a fixed amount of throughput at a per second granularity, and whenever a customer gets a spike in a given second, the budget from the minute worth of throughput is applied to that so that all the spikes are evened out. And this shows that you can make tremendous savings, and developers love this because they get predictable performance. At the same time, they can reduce they don't have to provision for the peak. Finally, running the service. So we run the service. The engineering team is the ops team. There's no ops versus engineering. We deploy the entire stack worldwide every week. We deploy new features all the time, and they are turned off or only enabled for a set of customers. This happens all the time. Every day, a 16-hour stress run. We run a 16-hour stress run, including, if Kyle is here somewhere, JEPSON tests. We run a linear usability checker on top of JEPSON tests. And we have all sorts of chaos, all sorts of customer workloads from first parties and external customers that we run. Another interesting thing and so only after all these gates clear, we can deploy. Another thing we have done is that we have added invariant checks throughout the code base. So anytime any invariant is violated in the code, we trace it out. And each of those traces correspond to a Sev2 alert. You have to wake up in the middle of the night. And over time, we found a pattern of all of those invariant violations have decreased. And the more and more tests have gotten added. And because of that, we are able to catch issues way before the actual SLA violations happen. We monitor this at a far smaller granularity. We monitor at 5-minute interval. The SLAs kick in at an hourly boundary. That's the billing window. So the bar for violations is far more stringent than what customer actually sees. If you're, highly recommend you use it. It's the most beautiful thing that ever happened to mankind. There's a link. I'll post the slides. There's a link to technical overview of Cosmos DB. Follow Cosmos DB on Twitter, and we are hiring. Thanks. Thank you.
So we've got time for a few questions, if anyone's got any questions.
Yeah.
Thank you for presentation. I have a question about how do you support schema versioning with schema?
Yeah, so Internally, we know the schemas of all the records that we have ingested, but you don't have to worry about the schema, or you don't have to put any versions. Every instance, effectively, every instance of a record that we ingest has a version, and we have the ability, because we extracted the schema out of all the instances that we have ingested. We have the ability that if you ask for a schema on a table, say, give me all the schemas that correspond to records which are in this table, we can extract them and return it back to you. So internally, we keep the track of all the schemas, but you don't have to worry about it. Does that make sense?
And how do you read them? If the schema is changed, how do you read it? How the client reads it?
The client just operates on records. Client doesn't have to know the schema of it. People ask for schemas when they want to build visualization frameworks and things like that, or build some entity mapping tools. But by default, the record itself, we assume that every record belongs to a completely different schema. Imagine every record consisted of GUIDs, right? The name was a GUID, the value was a GUID, and whatever level of nesting of that record was, it was all GUIDs. And we assume that worst case, and the fact that we find commonality of interior nodes in those trees is just a nice side effect, but we assume the worst. So every record is a different schema, is the assumption.
Hey, thanks for the talk. I like the way you provision with multiple granularities. Your most granular way of provisioning is by second, but of course you offer guarantees of sub-second latencies. What's been your experience with sub-second spikes affecting latencies?
Meaning provisioning throughput. If you provision throughput dynamically, how does it affect the latency?
You provision throughput at the secondly level, but they might exceed that at the sub-second level while remaining that at the second level.
Yeah, so whenever you exceed the throughput that you provision, so we allow you to elastically scale throughput by just calling an API, setting the throughput. But whenever within a given second, if you exceed, and if you don't have any other minute worth of budget available to you, we will rate limit you directly at the admission control. So at the admission time, if we have done all the charge calculations of within this second how much you have already consumed. If you want more, then in that second, we will tell you to retry after and send you far in the next second. And if you come harder and harder and harder, we keep sending you farther and farther in time. But we don't. Your point is very valid. That's the reason why the latency SLAs are not compromised, because we only serve as much as you provision, and for the things that we serve, we had the budget. Make sense?
We've got time for one more.
Hi, as a developer, I would like to know how difficult it is to migrate from a database, a MongoDB or SQL Server, to use this, and if I will have the same tool that we have for SQL Server that give us our life easier. So that's my two questions.
Yeah, so MongoDB is a lift and shift. It's the APIs are supported. Same with others like Gremlin for Graph or Azure Table Storage, and we are adding more and more. So those are easy. You can do it yourself. You just change your connection string, keep your app the same way, and point to Cosmos DB and continue to use your APIs. You get all the benefits of a robust system. For SQL, there are migration tools, so you can use those tools to migrate. I can send you links.
Okay, thank you very much, Dharma.
Thanks.